Hey, what's up guys? In this video, I'm just going to go over the first problem from Dr. Nero's practice exam. Now, I had originally planned on like just going through and doing the whole thing in one sitting, but that actually would probably take a while. Because, you know, this exam is designed to take 50 minutes, I believe. So, you know, don't let that freak you out or anything, but like as I go through, I'm going to be talking about like lots of conceptual stuff. So it's going to take me, you know, much longer to go through the exam than 50 minutes, right? Because kind of using this as a focal point, right, for your review. So we'll just do one problem at a time. And I think that if you go through and you watch all three videos, you know, I'll have one up every other day or so, let's say, you'll have like a good idea of what should be on your page of notes also, right? So that's another benefit to this. Okay, let's get going here though. So we're gonna do problem 1 today, which is just a charge, some point charges, right, distributed in sort of a certain way here. And I'm gonna go ahead and do something that I like to do to simplify the notation a little bit, right? So let's say, let's just define this. We're gonna say definte. We're gonna define Q with no subscript, right? To be 3.0 nanocoulombs, right? And you'll see why I want to do this in just a second. It's gonna help things a little bit with the notation. So this means, right, Q1 is just Q, right? Q2 is just negative Q, and Q3 is just 2Q, right? So you always want to be on the lookout for little notational things like this that you can do to simplify your work a bit. And so, you know, we'll see like as we get into actually solving for things that this is gonna, you know, make it a bit cleaner. Also, we have A is, let's say also, oops, A is 2.5 meters. And we're gonna just want to do like a quick bit of geometry here. And let's look at the picture just kind of in isolation here. So I'm going to zoom in a little bit. It's gonna get kind of fuzzy, but that's okay. So actually, I guess this isn't really much better. But anyway, it's fine. So the probably the simplest thing to do, right? The simplest way to kind of see what this distance is, say from like charge 3 to the point P or charge 1 to the point P or whatever, right? Is that this almost makes a square, right? And point P would be at the center of this square. So then we can argue, right, that the distance from 1 to P, the distance from 3 to P, and the distance from 2 to P are all the same value. Now, you know, maybe you could just kind of see that from the picture, right? But sometimes the diagrams can be like a little misleading, and you want to make sure that you just take a quick second to convince yourself that this point is in fact the same distance from all three charges. And so it is, right? And we can use, well, let's do this real quick. We're gonna call this distance right here B, right? That's the distance from 2 to P. And then we just argued that the distance from 3 to P should be the same as the distance from 2 to P. So we'll also call this B. And then we'll call this B as well, right? Just to be complete here. So the distance from 1 to P is also B. So we just have to use the Pythagorean theorem to solve for this, right? So let's do that. I'm gonna say b squared plus b squared equals a squared, right? That means that 2b squared equals a squared. And then this means that, let me not skip steps here because that's how I make mistakes, but we would write square root of 2b equals a, and then finally write that b equals a over the square root of 2. Okay, now this is great because now we have everything, right, in terms of two variables. We have everything in terms of Q and A, which is awesome. And that's going to make our work much easier to read and easier to simplify, right? And this is the kind of thing that your TA or your instructor, whoever's grading your work, is going to want to see. I promise you that. So now let's actually start doing some calculations here. So I'm just going to call the first part A. We have to find the electric force on charge 3. So let's look at our picture real quick, and I'm gonna expand on this a bit. We want to maybe go through and like just put a little indicator of what the sign of the charge is for each one of these, right? Because that's going to dictate which direction the electric field points. So this is a plus charge, right? Q1 there. Q2 is minus, and Q3 is positive. Right, so this is what I would do as I go through and solve this. I would just, you know, make little annotations on the diagram that's provided to help me kind of see what's going on. Now, let's try something here. We're going to draw the vectors in, right? So we want to find the electric force on charge 3. That means charge 1 is going to exert a repulsive force on charge 3, right? Because like charges repel each other. So let's do that. Let's draw an arrow in like this, right? This is going to be, let's call it E1. So that's the electric field due to charge 1. Okay, so that's good because I keep wanting to do electric field. This is true, but let's just talk about forces. So F1, right? Let's pretend that didn't happen. Okay, so this exerts a force F1 that points straight down on charge 3. And we know that for a configuration of two charges where one is positive and one is negative, they're going to exert attractive forces on each other, right? So what we're going to do is we're going to write that F2 should point this way, like so, right? And I'm trying to put this writing strategically so this doesn't get too cluttered, but I think it's just going to happen. Now, like what we can say about these two forces right now is that they have the same magnitude, right? Because charge 1 has the same magnitude of charge as charge 2, and they both are the same distance away from the third charge, right? So that's actually like a nice thing to notice, because let's say we just solve for F1, then we know what the magnitude of F2 is, and vice versa, right? So let's just do 1, and then we'll just sort of adapt our answer to write down what the other one is. So I'm going to just move this over real quick. Let's say then the force exerted by charge 1 on charge 3 is this. And I'm going to write it as a vector just to talk about some stuff here that we should be mindful of. So we have, I just said I was going to write it as a vector. This. Now, this is going to be negative, right? And that's because this force points in the negative y direction, as indicated by our sketch, right? And so we're going to write what the force is. It's just K Q1, Q3, right? This is the Coulomb force equation over a squared. And this is going to point in the y hat direction. And remember, all this crap here in the fraction is just going to be positive, right? So we just put a minus sign out in front to sort of force this to point downward. And then I have to go through and make this a unit vector because this looks gross as it is. So let's just do that. There we go. And then what we can do is we can just plug in some stuff, right? Because we know, let's see here, we know that Q1 is just Q as we've defined it, and Q3 is just 2Q. A squared is just A squared. And then this still points in the y hat direction. Let's just do that. And then we can write it one more time. We can write that this is negative 2kq squared over a squared in the y hat direction. Negative you know, a negative number in the y-hat direction, right? Which means it's pointing down. And this should be good, right? So I think that's all there is to this part here. And then what we're gonna do is we're just gonna use what we noted about the second force, right? Let's just say because of the symmetry, and you always want to be thinking about symmetries. We can write this. We can just write that F2 is going to be, and I should talk a little bit about what I'm doing here, because there is sort of a potential snake in the grass that could, you know, cause problems. So let's just talk about this also. I'm gonna write KQ1, oops, KQ1, nope, not that, KQ2, Q3 over a squared. But what I'm gonna do is I'm actually gonna put Q2 here inside absolute value bars. And this all points in the positive x direction, right? And so the reason that I'm putting Q2 inside absolute value bars is because we have that it's negative Q, right? And if I had not done this, then this would actually sort of be indicating that my force is pointing to the left instead of to the right. Okay, and we know it's pointing to the right because we argued that oppositely charged particles will exert attractive forces on each other, right? So that's why I'm doing this, because I just don't want to pick up an additional negative sign and have that like mess my final answer up, right? So this then is going to work out to be, we'll just plug in what we have. We have K and then absolute value of negative Q, right? Which is of course just Q times 2Q over a squared. And still in the x hat direction, of course, right? And then if we go through and simplify this, we find exactly what we expect, right? That this has the same magnitude as F1, which is 2KQ squared over a squared. And the direction is in the x hat direction. Okay, so this is good. The final answer, should just be expressing this as a vector, and I believe that you know, any instructor really is going to be okay with you doing this two different ways. One could be just expressing the components, right? Expressing the vector in terms of its components. The other could be expressing a magnitude and a direction, right? We're going to do the first way. We're going to write it as an ordered pair. I'm just going to write F equals F1 plus F2. Now these are all vectors, right? So let me just make them vectors. And I'll just write this as an ordered pair. And we're going to write that this is 2KQ squared over a squared for the x component, and then negative 2KQ squared over a squared for the y component. Now notice that you could actually go through and you could factor out 2KQ squared over a squared, right? And that's what simplifying the notation like we did does for us. So we could even write this. We could write something like 1 minus 1, and there you go. That should be your vector, your force vector. Let me just make sure before I move on that I didn't make any mistakes here. So we want the force on charge 3. This should be a repulsive force. This should be an attractive force. I didn't accidentally write A or any power of A other than A squared, right? Yeah. Because that's the thing you guys have to be careful about, right? You have all these formulas that look so similar to each other. So, you know, you really want to be on top of that, right? Being able to differentiate them and making sure that you're solving for the correct thing. So there's that, and this is not so bad, right? I think this is good. Okay, even if there is a mistake, right? This is the exact correct sort of approach to this. So, and I'm not going to plug numbers in because you know that's not something. Well, I don't enjoy doing it, if I'm being honest with you. And this is really the physics, right? The rest is just, you know, plugging things into your calculator. Okay, so now we have to figure out what the electric field is at point P. I think I might just clear this out and make another diagram here. So let's do this. I think this is probably fine. Okay, so we want the electric field. Oh, I do have to go through and now fix this. Just remind myself what this stuff is. See, this is why this is taking time, right? Because I'm trying to be careful and thorough. Let's see here. So then Q2 was negative, right? Yep. Okay. So now, the idea is that the electric field, points away from positive charges and toward negative charges, right? So I think that there's a way we can simplify this too, that I'll talk about using the symmetry again. But let's first of all just draw in the electric field due to Q3, right? That's going to point radially away from it. So at point P here, our electric field is going to look maybe like this. And we'll call this E3. Now I get to write E like I wanted to before. Okay, so then let's think about charge 1. This is also positive, so the electric field it generates will point away from it as well, right? So we could do something like this. We could write E1. Now, I'm trying to make this arrow a little bit shorter than the one that I made for E3 because E3 actually has double the charge, right? And if they are the same distance away, then its electric field should be twice as strong as E1's. Now, E2, right, the electric field due to the second charge is also kind of interesting because it is going to point in the same direction as E1 and have the same magnitude. So it's actually just the same vector, right? So if I draw this in, I'm not going to do this weird thing where I see people try to draw like vectors parallel to each other and stuff. I just like to do this because I think it looks much better. But in this case, let me say in this case, it's not just the magnitudes. We can actually write that E1 the vector equals E2 the vector. Right? And this is a pretty important thing because it's gonna allow us to just solve for one of these electric fields and then just double the result, right, in our final answer. So what we could even do, honestly, is we could imagine that this, one thing we could do, and it's okay if you don't want to do this, right? But one thing we could even do is we could just imagine that this charge isn't even here, and that this is actually 2q. Same effect, right? And you know, maybe this would be a good practice thing for you guys if you're not clear on why I'm saying this, to go through and just show that it works out to be the same if you do this. But we can even just imagine that all we have is two charges, charge 1, which is now 2q, and charge 3, which is also 2q. And look at this, right? This is also 2q. So look at how symmetric this works out to be. We don't even need to solve for the y component of the net electric field because we're going to have a cancellation in the y direction. So it really works out to be my net electric field is going to look maybe like this. It's only going to have an it's only going to have an x component, right? This is my net electric field. Now, if you went through and you cranked out the numbers, all that, whatever, you would find this if you did everything correctly. But like, if you can see it beforehand, you're going to save yourself a lot of work, right? So let's just figure out what this looks like. And what we're going to do is we're just going to solve for, say, the x component of charge 3's electric field, and then we're going to double that result, okay? So focusing on charge 3, we'll just write the magnitude here. E3 is going to be k 2q, and this is where we're using b now, right, over b squared. And that's, I guess that's it, right? That's just the magnitude of it. So then we want to break this into its x component, x and y components, technically, right? But this is where I might, you know, like in a high stakes exam situation, sort of like slow down a little bit and lose some time, because I would want to go through and make sure that I'm doing a very careful job of convincing myself of what's going on here in terms of the geometry. But what I would say is that this here, right, that I'm tracing out with my cursor, this here is clearly a right triangle. So that means that this angle and this angle must add together to 180 degrees, right? And they're actually the same angle, because as we were talking about, this is just a square, basically, with one of the corners missing. So that must mean, right, that theta must be 45 degrees if we call this theta. Right, theta is 45 degrees. So writing theta equals 45 degrees, we have, right, that the x component of the electric field due to charge 3 is just going to be what we have up there, right, 2kq over b squared times cosine theta. And cosine of 45 degrees is just root 2 over 2, right? It's one of the easier ones to remember because sine and cosine have the same value at 45 degrees, right? So this is just going to be 2kq over, and let's plug in what b squared is, right? B squared is a squared over 2, right? And then that looks kind of gross. Let me just fix it. And then cosine of 45 degrees, right, we said was square root of 2 over 2. And then I'm also going to be like very careful here because I'm so bad at fractions over fractions. So let me just make this easy for me to understand. So this is going to be, let's just say root 2 over 2 times 2kq. And then, let's see, division by a fraction is like multiplication by the reciprocal, right? So it should be 2 over a squared here. And then we're gonna have another 2 at the end. Let's not worry about that now, because we have to double it, right? But it's okay. So just in case you're not clear on why I said that, I'm saying because we are going to find the x component of E3 and then double that, right? So let's see here, what can we cancel? Well, definitely a factor of 2 can be canceled. Right, so we can get rid of, say, this 2 and this 2. And then what we find is that this is 2 square root 2kq over a squared. This is our x component, I do believe. Let me make sure I'm not doing anything silly here though before we move on. So b squared is definitely a squared over 2. Cosine of 45 degrees is definitely root 2 over 2. And then as I said, right, multiplication by or division by a fraction is the same as multiplication by the inverse or reciprocal. So I think this is good. I'm not going to promise you I didn't make an algebra mistake here, but like this is, the approach is solid, right? So then for the total field at P, due to symmetry, we just have that E, and let's just put a P here to indicate we're talking about the full field, equals 2 times the x component of E3 in the x direction, right? So I'll make this an x hat. And so this should just work out to be 4 times the square root of 2kq over a squared, x hat, right? Now, as a sanity check, right, this is going to work out to be a positive number, which is good, because we've kind of argued that this should be pointing to the right. And our dimensions seem to work out, right? Because the electric field looks like KQ over R squared, and this is just a pure number, right? This doesn't contribute to the dimensions, so we just have KQ over A squared times some failing or scaling factor, not failing factor. That wasn't a Freudian slip, I promise. So then this I think looks good. Let me just talk myself through this one more time, make sure it's good. So we just basically said that we can ignore charge 2 and imagine that the magnitude of charge 1 is doubled. So then this has charge 2q, this has charge 2q. Both of them are the same distance away from the point, so we just figure out what the x component of one of the charges is. We double that, and then we ignore the y component because the y components of these two will cancel out, right? As the sketch sort of indicates. Could have done a better job, but you know, I think it's pretty good. Okay, so that's that. Cool. Now, oh god, I haven't thought about dipoles in a long time. Okay, so I'm gonna write this as a vector also. The dipole moment is, let's do this. We're just gonna write px, py for the y, or for the x and y components, right? Like this. Okay. That's that. And we know what those are, right? Px is 3 times 10 to the negative 8th coulomb meters, and py is 4 times 10 to the negative 8th coulomb meters. So what is the force of a dipole? I think it's just, or the torque, I think it's just P cross E, right? But let me look this up because I don't want to lie to you guys, especially since this is an exam review. Going to Wikipedia, electric dipole moment. Yeah, okay, so let's say the corresponding torque is tau, right? This is what we use to represent, and is P cross E. So that, right? These are all vectors. So here's an interesting mathematical thing, right? Is that the cross product doesn't work in 2 dimensions. So what we have to do here is we kind of have to force these vectors to be 3-dimensional. And that's fine because we just say that their z component is 0, right? So if I rewrite this, I write px, py, 0, cross, and then our electric field is just, it just has an x component, right? Like this. And then 0, 0. Like so. Now the cross product, yes. I mean, I'm just gonna make Mathematica do it. But you should have, you know, like a formula on your equation sheet or something like that that reminds you what the cross product is, because, I mean, you can also calculate it using, what is it, the determinant matrix method, or you can just, you know, have the formula down, it doesn't really matter. So I'm just gonna make Mathematica do it though. So what is this? Is 4 times square root 2 times k times q over a squared 0, 0, right? So let me just remind you one more time. I have to, for the cross product to really work, I have to force these vectors to be 3-dimensional, and it's pretty simple because I just write 0 for the z component, right? Because like if I had, I'll just show you for instance, like if I had just written this, like written for Mathematica to take the cross product of two-dimensional vectors, it's basically saying, what are you doing, bro? So let me just fix that real quick. And there we go. We're gonna find that we have no dependence on the x component actually here. And this just works out to be negative 4 square root 2 kq over a squared py in the x hat direction, like this. And that should be good, assuming I didn't make any mistakes. Again, right, I'm not going to guarantee you that the algebra here is all 100% correct as I go through and do this, but like the process is definitely good, right? These things that I'm saying, especially about like simplifying your notation and looking for symmetries, these are super important and they're going to help you a lot. Okay, cool. So then, oh, you know what though? This is my bad. This is a mistake. Then this is something I should know better. This should be a z hat. This is in the z direction. Now, I was just thinking about that, right? Because I know that the cross product gives you a vector that is perpendicular to both the original vectors that you started with, right? And that means that if P lives in the xy plane and E lives in the xy plane, the only possible direction the cross product could point is in the plus or minus z direction, right? And this is something you should remember. And, you know, this is just like my intuition for the cross product sort of saving my ass here, because if I had, you know, accidentally wrote it to be in the x hat direction, I don't know why I did that, just like a brain fart or whatever, then, you know, if this was an exam, I would have lost a lot of points because whoever's grading my exam would have been like, oh, this guy doesn't even know, you know, either how to take a cross product or the fact that a cross product gives you gives you a vector that is perpendicular to the original two you started with, right? So you want to be thinking about these things. So that's it for this problem, right? We basically went through and solved it. And as I said, I'm just going to let you guys plug the numbers in. And I think that Dr. Nero will give the 175 students like the answers at least. But let's talk about like what we kind of need, what we kind of needed to do this, right? So for the equation sheet, you're gonna want the electric force and electric field equations, right? So the Coulomb force, we'll just call it FC, is going to be this. It's going to be K Q, and I'll just use little q big Q over R squared, and this points in the R hat direction, right? Like this. The electric field due to a point charge is just going to be KQ over R squared, right? And this also is going to point in the R hat direction. And this is why I keep saying you need to be careful, because like these equations look very similar, right? There's only one difference between them. And so you always want to be checking the dimensions or the units of your results, because they can tell you if you are wrong. They can't necessarily tell you that you're right, unfortunately, but they can tell you when you're wrong. And there's value to that. And then the final thing is that what we can see is that from these two equations, that there's a relationship obviously between the Coulomb force and the electric field. And that's just going to be that the Coulomb force is some charge times the electric field. So if you know the electric field at some point and you want to figure out the force on a charge there, all you have to do is multiply the electric field vector by that charge, right? So in my notation, little q is always going to be a charge that's generating an electric field, and big Q is always going to be a test charge, right? That can move and experience a force due to the source charges, right? The little q's. But you know, many instructors don't really follow that kind of a convention, and I sometimes forget to, but I try to as much as I can. So that's that. The important conceptual stuff for this is that like charges exert attractive forces on each other and opposite no, repulsive. God, why am I saying this? Maybe because, you know, like charges exert repulsive forces on each other, as we just saw, right? So two protons are going to exert repulsive forces on each other, and say a proton and an electron are going to exert attractive forces on each other. And let's say opposite charges exert attractive forces on each other. That's good. The electric field due to a point charge points radially away from positive charges and radially toward negative charges. And I guess finally what we can say is that having solved for the electric field at a point allows us to easily find the electric force on a charge at that point. Let's see, what else did we talk about? I don't think I need to write this down, but again, I just really got to stress you want to look for symmetry, right? Because this problem is full of it, and it can potentially make it way easier for you to solve, right? I guess the only other thing we needed was the dipole, right? So let's say a dipole is defined to be, I think this is how it's written. You might have a different formula, but this is fine. This is true, right? So remember, a dipole has let's say it's two charges, let's say 2-point charges of the same magnitude but opposite sign, right? So it could be a proton and an electron, for instance, right? And they're separated by a distance d. The vector d, right, as I've written it up there, points from the negative charge to the positive one, right? Let me just make sure that, and I should say an electric dipole, even though we haven't really talked about magnetic ones yet, but let's just put it in there. So it's just q times the vector, basically, that takes you from the negative charge to the positive charge, right? And that's what this vector here is. You know, we don't know what q is for this particular dipole, but it's okay because we have the vector explicitly, right? It's given to us explicitly, so we don't need to worry about what d is or what q is. It's just this is what it is, right? And then so let's say the torque on a dipole due to an electric field is this. It's going to be tau equals, we use this, right, P cross E. And this is a vector, right? Remember, cross products are vectors. And so what I'm going to do, I think probably the last thing that I'll do here is I'll just write out what this works out to be very explicitly for you. So we're just going to take an arbitrary dipole moment, right? Which is going to be px, py, pz. And then we're going to cross it with an electric field, right? Where the electric field could be three-dimensional. It's ex, ey. Easy. And I'm just going to make Mathematica give this to me as a column vector because it's a little easier to interpret. And the last thing I can do maybe is just make this substitution. I'm just going to make it use subscripts. So we're going to say that px is px, right? Py is py. I don't normally write things out using subscripts in Mathematica because sometimes it acts a little weird, but I think at this point it's fine. I hope it doesn't do anything crazy. And also, maybe you're noticing that I have to use epsilon for capital epsilon for E, and that's just because Mathematica interprets capital E to be Euler's number. So I have to kind of work around that in a sensible way here. And I think this is pretty good because they look exactly the same. Oh, and let me give it matrix form. So this is your answer. Right, like this. And you can go through and you can, write this in a different way if you want. You can put the, the positive terms in front or the plus terms in front, right? But this is what it's going to be. This is your cross product. And this works for, obviously, this isn't just for electric dipoles and electric fields. This is any kind of a cross product, right? That you could have. So there's this. Maybe we just talk really quickly about the potential energy, just in case that could come up. We'll say the potential energy of a dipole in the presence of an electric field is this. We'll just write U equals, and what is it, negative P. Now dot products, right, are a bit easier to crank out because it's just multiplying the x component of P by the x component of E, and then adding that to the y component of P times the y component of E, and so on, right? So what this works out to be is negative Px Ex plus Py Ey plus Pz Ez. Right, because these are vectors, this minus sign could just distribute, and this could just be written. I'll write it one more time, just because this is good for me also. I'm gonna put one more thing in here. So then what we would have, right, is we would have negative Px, negative Py, negative Pz, and then dotted with E sub x, E sub y, and E sub z. And I think that pretty much does it for this problem. Hopefully you found the video helpful. I will put out another one within the next few days going through problem 2, which is going to be, what is it, integrating, right? I think it's using an integral essentially to figure out the electric field of 2 quarter rings, right? One has charge positive Q, one has charge negative Q. But we'll get to that a little bit later on here. Okay, cool. I will see you in the next video then.